So welcome back, everybody, to Lecture 11 in CS170. So we're going to go on to a different topic today called dynamic programming. And this is going to be a general approach to many problems. And I'm going to describe it at a very high level and then go into the details. So we're going to solve a big problem by breaking it into smaller subproblems, and then solve the subproblems in order from the smallest ones to the largest ones. So you might say, this sounds kind of familiar. Why isn't this recursion? So let's do an example to distinguish this from recursion. And that's going to be computing a Fibonacci number. So here's the simplest recursive way you could compute a Fibonacci number. I'll define a function, fib of n. I need a base case, so if n is less than or equal to 1, return n. And else, return fib of n minus 1 plus fib of n minus 2. So what is the cost of this particular algorithm? And it's just the same as the cost of the size of the Fibonacci number itself, which is exponential, 1.6 to the n or something like that. So that's the recursive solution. So what would be the dynamic programming solution? We're going to solve the problems in order. So I'll define the base cases. Fib of 0 is 0, fib of 1 is 1. And then I'll just loop from the smallest problem to the largest problem. And obviously the cost of this is just order n. Now, how could we fix the recursive version in order to make it cost order n? In this particular case, there's a trick called memoization, where we simply record the fact that we've already solved fib of n minus 2, say, after solving fib of n minus 1, and we don't do it again. We just look it up. So that works in this simple case, but figuring out the right order in which to do the subproblems is one of the arts of doing dynamic programming. And it isn't always as simple as writing down the obvious recursive code and then saying memorization. So let's go on to some particular examples that are much more interesting than Fibonacci numbers. So we're going to start by looking at another problem that we've done before, which is shortest paths in a DAG, and we know how to solve that. We're just going to look at it again very briefly to see that it really was dynamic programming. We're just going to interpret it in that way to make sure that we understand the steps of dynamic programming in a simple case. The next new problem is going to be something called the longest increasing subsequence. So in this case, we're given a whole bunch of unsorted integers, and the goal is to find the longest subsequence of them that's sorted. So in this case, I think we can eyeball it. 2 seems intuitive. It's the smallest number, so we should start there. And then comes 3, and then comes 6. And then I could choose either 7 or 9. And in either case, the answer is going to be has length 3. So we're going to use that as kind of a toy problem to get started. They're going to be, then we're going to move into problems that are used every day and all sorts of different places. And the first one is called edit distance between 2 strings. And that's going to be defined to be the fewest number of edits to change one string to another. So what's an edit? It could mean, delete a character or insert a character, or substitute a character. So where do you think that is going to come up in practice? Well, the most obvious example is probably spell checking. You type something on your iPhone, and it's a word that the phone doesn't recognize, so it tries to find the nearest word to it in the sense that it requires the fewest edits. So another example is DNA. So how similar is my DNA to your DNA? So, and this isn't just used by companies like 23andMe, where you can find your relatives, but it's used in all sorts of scientific problems where people are trying to understand nature and in all sorts of different ways, and how viruses form, stuff like that. And so I'll say a little bit more about that later. And here's one other unfortunate example: cheating detection. How similar are two solutions? And that could be a problem. So that's one example. Another example that we'll go into today is knapsack. And so here is the maybe the traditional way of viewing it. We're given n items, and they have some weights, W1 through Wn. And they also have some values. Some are more valuable than others. And you have a total weight limit that you can carry in your knapsack. So the question is, how do you pick the subset of these items to maximize the value, but keep within the weight limit? So the sum over all items in the subset of the values with a weight limit. And so this could be referred to robbing a jewelry store, which is, I think where the name knapsack came from. And the jewelry has weights and values, or it could come from investing, where you're trying to decide how much, which investments to make that have certain initial costs, those are their weights, but they have certain likely payoffs in the future, those are their values. So how do you do the best kind of investing? Now, those are the ones we're going to do today. There are also going to be some other ones that will be gone into in the next lecture. And one of them, getting back to paths and graphs, is all pairs shortest paths. So you want to find not just the shortest path from one source vertex to all the others. You want to find all the shortest paths between all possible pairs of vertices. Now, you could obviously just run our existing algorithm. We know how to do Bellman-Ford to find the shortest path between one source vertex and everybody else, but we want to do better than that. So better than n times Bellman-Ford. And there's another one, which I'll just mention very briefly here, the traveling salesperson problem, TSP. So in that case, you have a salesperson who wants to visit every city in a list of cities to do their business and then return home. They want to visit every city once. That's the most efficient thing to do. And they want to minimize their travel time. So you can make that into a graph problem where you want to find a cycle in a graph that visits every vertex or city once and minimizes the sum of the edge weights. So there are lots and lots of these examples. And, I'm just going to do the first few today in lecture. Let's see. Subsequences might need to be consecutive. Well, so here, looking at this example, 2 and 3 are certainly far apart. That's why it's, can be a challenge, because they can be arbitrary distances apart. And I should say the answer is not unique. Let me just, because I could have 2, 3, 6, 9, or I could have 2, 3, 6, 7. So there are, multiple possible answers. So yeah, so the longest length here is 3. Okay, so let's take a look at shortest paths and DAGs from a dynamic programming point of view, and use that to illustrate the approach. There's going to be a 4-step approach that we're going to use for all dynamic programming algorithms. And since we know the answer to this one.
Hey, Professor, is it
yes.
a 4, the answer on the last for the subsequence?
Oh, I'm sorry. I was counting edges, and I should have been counting vertices. You're right. Let me just fix that. And I will write length equals 4 vertices, not 3 edges. Yes, my mistake. Thank you. Okay, so here, just to remind you of what a shortest path in a DAG is, we're given a graph, and it has no cycles, and it's given edge weights, W of E, and they could be an arbitrary positive or negative integer. And since we don't have cycles, it's no problem with having negative edge weights. And I want to find the shortest path from a source vertex S to some other vertex V in the graph. So here's going to be the approach from a dynamic programming point of view. So the first thing we have to do is define the subproblems that we want to solve. The smaller subproblems. And so for this one, it's pretty natural. It's going to be find the shortest path from S to some other vertex from the source to another vertex, I'll call it V prime, for V prime closer to S than V. So in this case, closer to is going to be our the way we consider what smaller problem is. So that's the first one. We define the subproblems. The second step is going to be show how to solve the real problem, the problem you want to solve, given solutions to the subproblems. Okay, so in this case, here's my source vertex. I have some paths to a bunch of other vertices, call them U and U prime, and there's an edge, excuse me, and there's an edge from U to V, and there's an edge from U prime to V. So those are my smaller subproblems, paths from S to U and S to U prime. So how do I figure out the distance to V? And this should look familiar from when we talked about this algorithm before. So the distance from S to V is going to be the minimum over all vertices, such that there's an edge from vertex U to vertex V of the distance to U plus the length of the edge from U to V. So I'll just take the lengths of these edges and add in those lengths and take the minimum over all of those. So that is going to be how I solve a subproblem. Those are the two hardest parts, but there's something else you have to do that's sort of straightforward. There's always a base case. You have to initialize things when the problems are as small as possible. So here is one base case that's pretty obvious. The distance from S to itself is 0. But are there any other base cases? How would there be another base case? So let me just draw a little picture here. So suppose I had a vertex W and one edge there from W to V. How would I initialize W? Well, I will set the distance to W from the source equal to infinity if W has no inward edges. So in other words, if W is a source vertex, it's obviously an infinite distance if it has no inward edges. So that's how the initialization is going to do. So there's one more step, which is figure out the order in which to solve the subproblems so that when you finally come to a problem, you have all the subproblems ready. So choose order in which to solve subproblems. And so the question is, how did we do that in the case of a DAG? We just did topological sort. Starting at S. And do them in increasing distance from S. So these 4 steps here, and let me just highlight them a little bit. So 1, 2, 3, and 4, define the subproblems, show how to solve a problem given the solutions to the subproblems, initialize the base cases, and choose the order. We're going to do those same 4 steps over and over again for every other dynamic programming algorithm that we're going to consider. So the question is, shouldn't it be if W is not reachable by S? Well, in that case, I would have, suppose there were a big, let me just address that. So suppose W were here and there were just a huge number of edges that were going off from W that eventually landed at V. You're saying I would have to initialize all those to infinity as well. Well, that's sort of running the algorithm. So that's not an initialization. The initialization is I just need to set W to infinity, and eventually the algorithm will set all the distances for all these other ones to infinity as well. Does that answer your question? Okay. So we're going to do these 4 steps over and over again, but let me just ask for a question here. So what if, instead of finding the shortest path, we wanted the longest path? How much would we have to change this algorithm? And the answer is not much. There's one obvious thing to do. We could just change all the weights to be their negatives, or we could change min to max. Either way, it all works. So, okay. So now let's go on and actually apply this to the longest increasing subsequence problem. And so here is a slightly different example. And so let me put in, let's just do this by eyeball first. And so intuitively, I could go from 1 to 2 to 4 to 5 to 6. And that would work. But there's another possibility too, obviously. I could go from 1 to 3 and then to 4 to 5 to 6. So the answer is not going to be unique. So let's do step 1, which is try to identify subproblems. And the most obvious thing is that let's let f of I be the longest increasing subsequence in the first I characters, the first I numbers. So x1 through x of I. Okay, so that's sort of an obvious way. We're just going to go from left to right. And now let me solve the big problem using subproblems. So the point here is that, let me give you an example and see if this works. So here's my sequence of numbers, 5, 6, 7, 1, 2, 3, 4. Okay, so what's the longest? So what's F1? That's the longest increasing subsequence in X1, and that's obviously just 5 all by itself. What's the longest increasing subsequence in X1, X2? 5, 6. In X1 through X3, 5, 6, 7. Now I tack on a 1, the answer is still 5, 6, 7. Add the 2, still 5, 6, 7. Add the 3, it's still 5, 6, 7. I add the 4, and suddenly it all goes away, and the answer is 1, 2, 3, 4. And so I didn't define the subproblem, right? Because I didn't have enough information by the time I got to the end to actually solve the problem. So let me just say that this was not the right answer. Okay, so the point here is that, there's some art in picking the right subproblem. So let's try again. So I needed some more information in my subproblem. I needed to know not just, where, how long it was. I needed to know how it ends. So let me do it this way. So I'm going to let L sub I be the length of the longest increasing subsequence in X1 through Xi, and it ends in I, in X sub I. So X sub I has to be the last one. Okay, so that's going to be my subproblem. So now, how do I solve using subproblems? So now I've solved, I know what the longest increasing subsequences are that end in X1, X2, X3, all the way up to X sub I minus 1. And so now I add a new character. And so the answer is going to be, well, I could always just take X sub I all by itself. And so it's always, the answer is always at least 1. That's not very interesting. But how do I know whether it's worthwhile adding X sub I to the end of a list that I've created before? Well, I'm going to have to look at all the lists that I've created before. So I'm going to look over all these shorter lists. That's j less than I. And I'm going to take the length of that list and add 1 to it. But there's a condition. When am I allowed to add when am I allowed to add xi to the next list? It's only if x sub I is bigger than x sub j. If adding xi keeps it to be an increasing subsequence. So that is going to be, let me add one more parenthesis there. That is going to be how we solve. And I'll run that algorithm on this sequence up there in a moment. So what's the base case? That's pretty easy. Just if I have one character, the longest increasing subsequence is 1. And the order to solve is quite straightforward, just by increasing I. So let us run that on this sample here. And so let me just write it down again. 1, 3, 2, 7, 4, 5, 6. And let me use a different color. So the longest increasing subsequence with 1 is 1. And then when I move on to 3, excuse me. When I move on to 3, then there's an increasing subsequence. That's the longest path that ends in 3. What about 1, 3, 2? What's the longest increasing subsequence there? It's going to be 1, 2. What about 7? Well, it could be 1, 2, 7 or 1, 3, 7. Both of those are possible. Then there's 4, and that could be 1, 2, 4 or 1, 3, 4. And then once it ends in 4, I can just go to 5 and I can go to 6. And so that illustrates how the algorithm would be run to get the right answer there, which is now 4. And let's just see what is the cost of this algorithm. So at each step, there are n steps because I'm just going from left to right from I equals 1 to n. And what is the cost of each step? I have to look at all the previous steps. I have to look at all of the j less than I. So the cost at each step is order I, and that's order n squared. So that is the simplest way to do it. Now, let me make another observation here. So I've drawn something in red, and what are all these red edges? They form a DAG. There's always an edge from a smaller value to a larger value. Well, I've left out some red edges, but so there's always an edge from xi to xj if xi is less than xj. So we can think of that being a DAG. And what we're really doing is finding the longest path from the DAG. So this is very, very similar to the algorithm we just talked about on the previous slide. It was just sort of doing the same thing in disguise a little bit. Okay.
Professor, there's a
Yes.
question in the chat actually about how you were able to choose 1, 2 instead of 1, 3 for the base case of the subsequence.
So when I get to 3, so I'm iterating from left to right, and when I get to 3, then the answer is 1, 3, and so that I can record, at 3 that. So when I get to 3, I'll record both the length, and somebody asked, don't you want to know which are the previous ones? Well, then I can create a backward edge if I want. So I could create, for example, an edge from 3 to 1, so I can keep track of what that longest path is. So that doesn't increase the cost. It's still an order n squared algorithm. Then when I get to 2, I will look back, and I will see that, well, 1 came before me, and so I could tack 2 on the end of 1, and that is another one that I could get. So I could get 1, 2. And so, and then I keep moving forward, and at the end, I can see that there are 2 ways to go back. I could have 1, 3, 4, 5, 6, or 1, 2, 4, 5, 6. So the answer will not be unique, and that would be traced back by these green edges. Okay. That answer the question?
I don't see any more questions, so I think
Okay.
so.
Let me move on.
There's also a question, sorry, Professor.
Yeah, go
There's
ahead.
also a question about explaining the max 1, max L of j plus 1 part.
Okay, sure.
Yeah,
So where did this come from? So remember, L of I is the length of the longest increasing subsequence in x1 through xi, but it has to end in xi. Xi has to be in the list. And so then when I say, okay, I've figured out the longest paths before me, how do I know whether I can make it longer when I get to xi and add it to the list? Well, I could always choose xi to be a list of length 1. That's sort of always possible. And then I could also look at all the ones before me. So x1 through x2, x1 through x3, x1 through xi minus 1, and ask, if I added xi to the end of those, would it still be increasing? So this is asking, would it still be increasing if I added xi to the previous ones? And I look at all the possible lists that I had before and pick the longest one and add 1 to it. Yes, so that makes sense? How would this solve 5, 6, 7, 1, 2, 3, 4? Well, by the time I got to, okay, let me just write that down. So the answer would be the longest increasing subsequence that ends here has length 1, length 2, length 3. This would be length 1, length 2, length 3 again. And when I get to 4, I look behind me and I see that I'm only bigger than this one. So it would be 3 plus 1 or 4. Because this, is xi bigger than xj would only apply to that comparison. Is 4 bigger than 3? Okay. So the next one is edit distance, where I have two strings, call them x and y, and I want to know, okay, another question, is max applied to L sub j plus 1 as well? Well, the max is applied to L sub j plus 1, yes. That's the length of all the previous ones, with adding xi to the end. Okay, let me continue here. So I have two strings, x and y, and x consists of n characters, x1 through xn. So you can think of them as letters from the alphabet. And y1 could have m characters. They don't have to be the same length. And I want to know how similar are these two strings. And the way I'm going to measure their similarity is I'm going to count how many edits I need to change the string x to string y. And what edit means is I can either insert a character into x, I can delete a character for x, or I can change a character in x, substitute a character for an existing one. So let's do an example to make this kind of concrete. So I'm going to ask, how far apart are the two words snowy and sunny? So which have something in common. And so the way I'm going to do this, I'm going to give you two illustrations of a sequence of edits that change snowy into sunny. And so the first thing I could do is take the character snowy and insert an S in front of it. And I'm going to, so this is saying, please start by adding a character S because sunny begins with S. This is kind of silly because so does, snowy, but I could do that. So now I look at the next character, which is the S in snowy and the U in sunny. And so this had a cost. So I'll just do a +1 there because I had to insert an S. So now I'm going to change the S to a U. That also is a cost. So that's a substitute. So what's the next letter in the two strings? There's an N and an N. Great. I don't have to do anything. They match. Then I get an O, but that doesn't appear in sunny, so I have to delete it. So I'm going to indicate that there. So that's a delete the O. That cost me something else. Then I have the W, and I have to delete that too. And then finally, I have to insert another N because there's an extra N in the word sunny. And then finally, the Y's match. And so I don't have to do anything. And I've changed snowy into sunny by this sequence of inserts, deletes, and substitutes. So the number of edits here equals 5. But that was kind of a silly way to do it. Let me do a better way. And so I could notice that, well, they both begin with S, so I don't have to do anything there. Then I have to insert a U because there is no U in snowy, so I better put it in there. Then the next two characters are N, so that's good. So that's going to cost me a +1. The N's are the same, that's good. Then I have an O and an N, and I have to substitute, I have to change the O to an N. So that's a +1. Then I have to remove the W, and then the Y's are the same. And so now I've done better. The number of edits is 3. But the answer is not unique. So let me just show you another way to do it with 3 edits. The S's are the same. I'm going to have to insert a U, no choice there. The N's are the same. Then I'm going to delete the O because it doesn't appear in sunny. And then I'm going to change a W to an N. And then the Y's are the same. And so again, I've gotten the number of edits equals 3. So there is not a unique answer. So what I'd like to do is given two strings of arbitrary length, which could be words or DNA sequences or whatever you like, I want to measure how similar they are by counting the minimum number of edits to change one to the other. So here are the motivating examples. Spell checking and suggesting fixes. Find the closest words and have your, your iPhone suggest that you fix that. Then there's DNA matching, as I mentioned before, cheating detection, and also spam filtering. Looking for similarities between this likely spam and some previous spam. Okay, so now let's do the 4 steps again. What are the subproblems we need to solve? How do I solve a problem given the solutions to its subproblems? What's the base case and what's the order? Okay, so this is going to be the 4 steps to find the edit distance, ED, between these two problems. So here are the subproblems. So here is going to be something that's maybe a little surprisingly more expensive. So what I'm going to do is look at all the leading subsequences of X and Y, because I don't know, whether the beginning of X matches Y or the end of Y or whatever. So I'm going to have sort of a quadratic growth in the number of problems that I have to look at. So for all of the length I subsequences of X and all of the length J subsequences of Y, what I'm going to do is compute F sub ij, which is going to be the edit distance between x1 through xi and y1 through yj. Okay, so I'm going to have m times n subproblems that I want to look at. Okay, so the next thing is, suppose I figured this out for shorter substrings. How do I, use that to solve my longer one where I'm adding a character? So what I'm going to do is look at the last character in the optimal alignment and ask how could it be formed? There are 3 possibilities. So now what I want to do is solve the problem Fij, the edit distance where I've adding an extra xi. So it could be that the best thing to do is just remove xi. That's the notation I used before. Xi is in the string, and I'm going to remove it. So remove xi. And what is the cost there? It's going to be the cost of making the first I minus 1 characters of X perfectly match the first J characters of Y, and then removing Xi. And if I remove Xi, then the first I characters of X will perfectly match the first J characters of Y. So that's one possibility. The next possibility is that I insert Y sub J. And this is a notation I had for that before. So what's the cost of that? It's going to be making the first I characters of X perfectly match the first J minus 1 characters of Y, and then removing Yj. So the other possibility is that I've perfectly matched the first I minus 1 characters of X, the first J minus 1 characters of J. And so that's going to have cost me F sub I minus 1 comma J minus 1 to match the first I minus 1 and J minus 1 characters. And now I look at the next characters of both strings, Xi and Yj. And the question is, what do I do to add that? Well, the answer is it costs me nothing if they're the same. That's the good news. If xi equals yj, if they match, it's free. And it's 1 if they differ. And so I'm going to call this quantity here delta ij. Which equals, just to repeat, 0 if xi equals yj, and 1 if they're different. Okay, so I'm going to call that quantity there to make it cheaper. So now, given all of those three possibilities to make characters x1 through xi match characters y1 through yj, how do I choose among them? Well, I'll choose the cheapest. So I'm going to take the minimum over all these possibilities. I'll either choose a minimum of removing xj, removing xi, inserting xj, or possibly substituting yj for xi. Now I'll take the minimum of those three. Okay, so are there any questions? What is the optimal alignment, the wanted result? It's, I start with x, and I want to do as few removes, inserts, and substitutes as possible to get to y. How far apart are the two strings? So now I have a base case. And the base case is going to be, I have a string of x1 through xi, and I want to have it match the string that's empty, 0. And that obviously is I, and they're all deletes. I just delete xi minus 1, xi minus 2, and I of them, and I finally get to a string of length 0. That's a very trivial base case. And similarly, here's the other base case. F of 0 comma j equals j, and they're all inserts. So I start with an empty string, and I want to make it match x1 through xj, so I have to insert y1. I want to make it match, the string y1 through yj, so I have to insert y1, y2, all the way up to yj. So those are the base cases. And finally, I have to say, what is the order in which to solve them? So, and here, I'm going to draw a picture on the next slide. Yes, question?
Austin.
Yeah.
Sorry?
So what are the two arguments in this f function?
Say the two arguments in which function? Say again.
Oh, sorry, I didn't realize we were unmuted. I apologize.
Oh, okay. So for f sub ij, what do we need? Well, let's just look at this formula up here. What we need are three previous ones, but it's not a simple linear order the way it was with the previous examples I've looked at. I need all of those in order to do it. So what I want to do now is draw a picture of what that looks like, because now it's not going to be sort of one-dimensional, it's going to be more two-dimensional. So are there any more questions? Okay. So here is a picture of the order of the subproblems that I need. And I've drawn it because I'm trying to compute this, if you like, two-dimensional array, f of ij. And so I'm going to need it. So I'm going to represent that as this grid, this n by m grid. And each of these boxes is going to hold f of I comma j. So this box here is where f sub j is going to live. So I'll just draw a little arrow there. So that's where f sub ij lives. And so what do I need to, and here's the formula from the previous slide. And so what values do I need? I need f sub I minus 1 comma j, and that is this value. That one lives there. I need f sub I comma j minus 1. That one lives there. And then I need f sub I minus 1 j minus 1. And that one lives there. So I need those three values. And I've drawn arrows to indicate that there's a DAG indicating the order in which I have to execute this. So the question is, what's the right order in which to evaluate all of these boxes so that when I get to this particular box here, I have all the data that I need? So what's a sort of a natural order to do this? Well, I could do it row-wise. If I compute the first row first, well, the first row I'm going to fill in, that's the base case. So let me indicate that. I've done that below, but this is the base case. So that's the base. So I've already filled in the first row and first column. So the first thing I'm going to do is then start working on the second row. And when I'm in the second row, if I just go left to right, I have all the data that I need. And then if I do the third row, I'll have all the data that I need. But I could also do it column-wise. And in that case, the first column is all filled in. Then when I get to the second column and do it from top to bottom, I'll have all the data that I need, and so forth. So how do we choose? We'll see in a minute that there can be a big benefit if you choose the right way to do it, row-wise or column-wise. It won't change the cost necessarily, but it could change a lot the amount of memory that you need. So let's try to run this algorithm, at least for a few steps, on converting snowy into sunny. So just to remind you here, so this is going to be our destination. So that's going to be the y, and x is where we start. We're going to start with sunny. So I guess I'm doing this backwards from the way I did it before, but it's okay. So we would get the same answer. So when I initialize, that means I'm going to fill in the first rows here just this way. And so what does that mean? That means that in order to get the when I go from here to here, that means I'm starting with an empty vector x, an empty string x, and I'm inserting the first character of y, the second character of y, and so forth. So going in this direction means I'm inserting a character. And going down this way means I'm deleting a character. Yeah, so this is the y-axis and this is the j-axis, if you like. And similarly, I'm going to fill in the first row of this. And it's going to be, just also done this way. So here, this corresponds to, I have an empty string, and I have to delete all the characters in X to get down to the empty string. So if I start with sunny and I want to get to a completely empty string, I have to delete 5 characters. So these are all sort of base cases. So let's fill in this one first. We have to fill this out first, whether we're doing it row-wise or column-wise. And so what are my choices? I could either take this number and add 1, that would give me a 2. Take that number and add 1, that would give me a 2. Or I could say, well, let me just compare the first 2 characters and say, are they the same? And the answer is yes, there's S and S. So that means I would fill this in with a 0. Okay, so then, so now I have the strings SS, and now I want to ask, how do I make it match, SN to S? Well, so I could take this one and add a 1 to it, oops, and get a 3. Let me undo that. So I could either do 2 plus 1, 0 plus 1, or I could compare N and S, and that wouldn't work so well. So here I would get a 1 by going in this direction. So that's the optimal choice there. And if I keep on going in this direction, I'll get 1, 2, 3, 4, because I keep deleting characters to get down to a single S. And here I'll keep adding characters to start with S and adding NOWY. So then I just keep on going. And, so here I would compare 1 + 1, 1 + 1, and 0 + 1. And I would get a 1. And by the time I work my way all the way down, I won't bother filling it all in. I get a 3 there. And so that is the way the algorithm would work. Shouldn't it be 2 for S, 0? So yes. Let's see, what am I doing here? Zero, 1, 2, 3. I think this is right. So I invite you to fill it in yourself, but I think I've done this correctly. 0. Okay, well, maybe not. 0, 1, 2, 3, 4. Let me just check. This should be, yes, sorry. Let me fix this. That should be 1, 1, 0, 1, 2, 3, 4. Yes, because here this 2 is gotten from adding a 1 to the 1 right next to it. Okay, so now I believe it's correct. And I will thank you. You're filling it in correctly and doing bug checking on me. That's very appreciated. Okay, so finally we get down to a 3 at the bottom, and that's the optimal edit distance between snowy and sunny. Now, what is the cost of this? And in time, it's going to be n times m, because the size of this array is by construction n by m, and filling in each entry is constant time. But the other question is, what about the memory? I don't want to store this entire m times n set of numbers, right? I want to use as little memory as possible. So the question is, how much memory do I need? Well, if I do it row-wise, I need to keep the first row, and then I can fill in the second row. But then when I'm done with that, I can throw away the first row. And then when I do the third row, I need the second row. But when I'm done with that, I can throw away the second row. So I could do it in time, in just by doing it, keeping a size of length m. Let me indicate that here. So it would be size m if I do it row-wise. But what if I did it column-wise? I could do the first column, then the second column, then the third column, and only keep the previous column. And so that would be n if I did it column-wise. And so it's going to be the minimum of these two. I'm just going to, take the minimum of m comma n, and that'll tell me how much memory I need. Okay, so are there any questions about this? So I want to mention that implicitly, you can think of this as a shortest path in a DAG. So why is that? So I've drawn all these arrows here, and they appear everywhere in the graph, but I've also associated weights to them. And what are the weights? Well, they're +1 for all of the edges that go from left to right. They're +1 for all the edges that go from up to down. And there's delta ij for all the diagonal edges. So for example, in this one, this edge has length 0. This edge has length 1. And all the other edges are sort of, similarly labeled. And so that means that I've implicitly built a DAG, and I'm looking for the shortest path in this DAG. So we're really solving that same problem in disguise. With edge weights, horizontal is always +1, vertical is always +1, and this direction is always delta ij, which could be 0 or 1. Okay. So this is the sort of standard solution, but there are some special cases that are worth knowing about where you can do it more cheaply. And so the motivation for these special cases are, I said the cost was going to be order m times n, but what if m times n are on the order of 1 billion? So who has to solve this problem? And this is where sequencing DNA comes up. Because the number of amino acids, ACGTs and so forth in everybody's DNA is around, 1 billion or on that order of magnitude. So why, if we want to sort of match people's DNA, then it looks, if we just use that algorithm I told you about, the cost would be 1 billion squared, which would take much too long for a company like 23andMe or anybody else to solve that problem, actually. So, but the good news is that any two people, how different can their DNA be? And the answer is, it's about 99% the same in their DNA. So most of our DNA is all identical, and that last 0.1%, has a very interesting story to tell. That's the differences among all of us. And so what that means is that the edit distance is going to be an order of magnitude smaller. It's going to be about 0.001 times 10 to the 9th, or order 10 to the 6th, in order to change, make one DNA match another. So how do we take advantage of that in order to do make this algorithmic cost much smaller than m times n, or 10 to the 18th? And so here is sort of a picture of how that works. So here is the same kind of graph that I had before, and the table that I had before, and now implicitly there's 10 to the 9th rows and 10 to the 9th columns. But suppose I know that there are at most 10 to the 6th edits necessary to get from one to another. What does that tell me about which subset of all of these 10 to the 18th, let me write this a little bit more clearly, of these 10 to the 18th cells that I need to evaluate? Well, here's the idea. Let's suppose I started just doing inserts and moving sideways here, then I wouldn't ever need to do more than 10 to the 6th. And if I started doing deletes, I'd never need to do more than 10 to the 6th deletes. And so in some sense, I never need to look at these huge corners. I only need to look at this tiny little band in the middle. So this is where you have at most 10 to the 6th edits. It's in that band. And so we only need to compute f sub ij for I minus j is order 10 to the 6th. And so that implies that the cost is going to be, order 10 to the 6th times 10 to the 9th, which is a factor of 1,000 smaller, order 10 to the 15th, which is still a lot, but it's a whole lot better. And this is obviously an important problem. And the name of the famous algorithm that people use for this is called Smith-Waterman, which you can look up if you like. And it's based on an earlier version of this by two other folks called Needleman-Wunsch. And since 10 to the 15th is still very large, there's been a lot of effort into coming up with parallel algorithms to evaluate this very quickly. And there's a big project here at Berkeley to make that work if you want to run this in parallel on big supercomputers. And the name of that project is called MetaHIPMER, which is run by our faculty colleague, Kathy Yellick. So if you want to learn more about how this is used in practice, feel free to look those up on Google. So let's see here. Are there any questions?
Yes, Professor, there's a couple of questions. I
Okay.
think the earliest one is asking about the edit distance question. Could we solve this using a graph, copying, and constraints?
Graph copying and constraints. I'm not quite sure what that means. Could you,
yeah, can whoever asked clarify,
could you elaborate?
please? Until then, there's also a question about, so there's only not the whole 2D array is being used at one time for the edit distance question.
Right, you only need a row or a column, or 2 rows and 2 columns. And in fact, in this particular example, you would only need much less. You'd only need about 10 to the 6th rows or so at any one time. So it's much, much smaller. Or 10 to the 6th entries in a column. Yeah, so this is much memory cheaper than before because you never touch this stuff out in the corners.
Cool. There's also a question asking, don't you need the neighbors of the edge elements in this part of the matrix?
So the thing is that at some point you say, if I go out here, then I don't really need any of this stuff. So you're sort of, this is an approximation, but yeah, you just don't bother computing these entries at all, and just use the 2 neighbors for which you have the data.
Cool.
Because the only way you could have gotten out here is to do more than 1 million edits. So 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 you sort of know just from the biology that none of these matter.
And then there's one last question. Can we use each edit as a vertex and run BFS?
So maybe that's referring to my comment here that we're implicitly finding the shortest path in a DAG with these edge weights. So since this is such a structured DAG, all of the, there's one vertex for each box in this grid, and there you only have edges that connect these nearest neighbors like that. Then constructing that structure is known implicitly, so we don't need to actually build a graph. I just mentioned it's analogous to finding the shortest path in a DAG, but the DAG is so structured, we only need to keep 1 row at a time or 1 column at a time, and that's all we need to remember.
Doesn't look like there are any other questions in the chat.
Okay.
Thank you, Professor.
Okay, so let's see how long it takes me to do knapsack. So here is just setting up the problem. Suppose you are robbing a jewelry store. And what you have is a knapsack. This is where the name of the problem comes from, that can carry, let's say, W pounds of loot. And you have to choose among the following possibilities: N joules with some values, V1 through Vn, and weights, W1 through Wn. And so the question is, which joules should you pick? And so what we want to do is pick a subset. Let me write it this way. So what I want to do is pick a subset of the joules, which I'll write as a subset of the integers from 1 to n, such that I'm going to maximize the value so that's the sum over all the values in there, subject to this limit, that the total weight is bounded by W. So that's one version of the problem. So, but instead, let's suppose you're deciding how to invest. And what you have available, you have W dollars to invest. And what you have to do is choose among n investments with likely payoffs given by the V's, and with costs given by the W's. Which should you pick? And it's the same answer, same formulation of the problem down here. You want to pick a subset that maximizes the value given your limit on what you're allowed to invest. So that's the knapsack problem. And so let us ask whether a greedy algorithm works. And after all, if you're investing or robbing a jewelry store, greed seems like a natural algorithm. So let us try this very simple case where you're allowed to have, let's say, 20 pounds. And the first jewel has weight 11 and value equals 15. The second jewel is not so valuable, it's 10, but it's much lighter. And then the third jewel is a copy of the second jewel. So what should you pick? And so I think that intuitively, then it's pretty clear the best you can do is pick these two because their weights add up to the most you can carry, and the value is bigger than the other one. And if you pick W1, then that would be all you'd be allowed to fit because you couldn't put either of the other two jewels in there. So that would be much worse. So what would greed give you? So if there are two greedy algorithms you can imagine. You could choose the jewel to maximize the value. And that leads you to a total value of 15. And that's less than the best, which is 16. Or you could choose I to maximize a slightly different quantity, and that's the value per weight. So that's a perfectly, the dollars per pound. That seems like a perfectly natural choice too, but that also leads to just 15. So a greedy algorithm does not work here, and we have to do something more clever. So what we're going to do is knapsack by dynamic programming. And so again, it's a 4-step process. What are the subproblems? So my problem is going to be to compute the maximum value where I'm allowed to pack a subset of 1 through I. So I'm only allowed to look at the first I joules, and with weight, maximum weight of U, which is going to be something less than W. So you don't get to use all your weight, and you don't allotment, and you don't get to use all the joules. It's just joules 1 through I. That's going to be the subproblems. And so how do I solve the problem that I want, given that I've solved all the smaller problems? Well, here's the idea. So the first one is going to be, well, if WI is too heavy, then I'm just not going to use it. So in this case, if WI is bigger than my allotment, so WI is too heavy, I'm just going to use the previous solution. So I'm going to, just look at item joules 1 through I minus 1 and use all my weight allotment U to pack them. Else, I could pack WI, and so I have to decide whether to do that or not. And so there are two choices. And so I'm going to pick the better of the two. So the first one is that I don't pack it. So don't pack WI, or I do. So what does that mean? That means I'm going to get the value of the ith joule plus the best I can do with whatever weight is left over, looking at the previous I minus 1. So I'm only going to look at the previous I minus 1 joules and how much weight is left to pack them. It's U minus WI. That's how much of my allotment I've used up. And so this is when you do pack WI. Okay. So that is how we're going to set it up. 3, what's the base case? If I'm not allowed to look at any joules, then it doesn't matter how much weight I have. The answer is no value. And if I'm allowed to look at joules 1 through I, but I'm not allowed to carry anything, then I also don't get any value. And finally, what is the order? And here, the order sort of follows again by looking at the dependencies. In here, I requires I minus 1. And it also requires, and U also requires the earlier value, lower values of U. So here's going to be my order. It's just going to be 2 nested loops for I equals 1 to n. And then for U equals 1 to W, the maximum allotment, then I just evaluate that formula. F sub I comma U equals ... The same formula I had in step 2. So that is going to be the algorithm. And so the last thing I want to ask about this is how much does it cost? So let's look at this code here. So I've written out the code entirely to make it easy. So I begin by initializing all the values of F sub I comma 0 to 0, all the values of 0 comma U to 0. So these two inner loops are cheap. And then here is the code for everything else. I'm looping from I equals 1 to n, from U equals 1 to W, and then I evaluate that inner loop cost. And so what is the cost of this? The inner loop itself is order 1, and then I'm doing it n times W times. So it's pretty easy to see that the total cost is order n times W. And so the question is this a polynomial time algorithm? Now, let me be a little careful here. What does polynomial time mean? It's asking, is it polynomial time in the size of the input? So what is the size of the input? Well, I do have n joules, and that's fine. So there's going to be some n in there. But what is the input? The input are these values, V1 through Vn, W1 through Wn, and then capital W. Okay, so what is the size of the input? So all of these, so it's going to be n times, and let me just take the largest V. So if I take the largest V, how many bits do I need to store that? And the answer is log base 2, right? Because these are just some numbers, and that's how many bits I need to store them. And if I assume that all these weights are smaller than capital W, it's the same story. It's log base 2 of capital W. So that is the size of the input. And so now let's observe that n times w can be exponentially larger than this. Because I have a w in this cost and a log w in this cost, and w is exponentially larger than log w. And so this is actually not a polynomial time algorithm. And that shouldn't surprise us, because in chapter 8, we will see that knapsack is NP complete. So nobody is ever likely to think up an algorithm that does not take exponential time to solve this problem. And that's going to be a chapter 8 topic. Okay, so that ends today's lecture. And next time, there are going to be a lot of other examples of dynamic programming, but that's all I wanted to say today. So are there any questions? Let me see here. Are all dynamic programming algorithms iterative? Well, let's see, it depends on what you mean by iterative. I've had a whole bunch of nested loops for these. Like this one here is obviously nested loops, but sometimes it's better defined by topological sort on a graph. And whether you call that iterative or not kind of depends on your point of view. But there is some linear ordering in which you do things. What is the difference? Oh, can you explain how you got, let's see, let me try to order this. Can you go back to slide 11? I'm not, okay. So, but the other question was, how do you get the logarithms in the runtime again? So there are no logarithms in the runtime. The runtime here is n times w. Let me just, so the runtime is n because the outer loop goes from 1 to n, times w because the inner loop goes from 1 to w. And so that is the runtime. So the question I was asking was, is this a polynomial time algorithm? And by that, I mean, is this function a polynomial in the size of the input? That's the question about whether an algorithm is polynomial time or not. And the thing was, the size of the input depends on log w, because that's how many bits you need to store w. But the algorithm runs in time w, and w is exponentially larger than log w. So this is the size of the input. The running time is this. So yeah, so there are no logs in the runtime. Yeah, that's just, if p were equal to np, then yeah, there would be, but that's not true as far as we know. Are we basically, what's the difference between dynamic programming and recursion again? Well, going back to the very first slide, sorry. Okay, here we go. So here is the recursive Fibonacci, and here is the iterative Fibonacci. And I said that we could make this iterative, this recursive version have the same cost, order n, as the iterative algorithm if we use this trick called memoization. And that means whenever we call fib on something, we store it, say, in an array. And if we ever need to call fib on that value again, we look it up in the array and say, do I already know this? That's what the memo is. In that case, you don't bother doing anything recursive. And so it works for fib, but it's sort of an expensive general fix, and it may not work terribly well for everything else. And sometimes the algorithms are much easier to understand when you write them down as iterating over the entries in an array. Are we basically sacrificing space complexity for runtime? And if that's the question here with memoization, it wouldn't be the case, because we just have one word in our memo, or just one entry in our memo for every previously solved problem. So for fib, it wouldn't matter. It would matter for knapsack quite a bit. it would matter enormously for the DNA case, because here I said that the cost of memory is just the minimum, the minimum of M and N, the minimum of the number of rows and columns. That's all we need to store. Whereas if you just did something naive with memoization, it would store the entire M times N array, and that would be a huge waste of memory. Why are we deciding, let's see, on slide 3, step 2, in the procedure, the same as the update procedure in Dijkstra? Well, yes, so this is shortest paths. So we are really just rediscovering, reinterpreting Dijkstra, but I'm doing it for a DAG. Dijkstra works for arbitrary graphs. And the reason I'm doing it for DAGs is that we want to be able to solve the subproblems in a given order and know that when we're done. And so that's why I can do this topological sort. So that's what makes this different from Dijkstra. But this inner loop, I think we called it update in the Dijkstra lecture. It's the same thing. Why are we deciding input size by bits in the knapsack problem, but not in other cases? So actually, in the other cases, the cost here was order n, and the size of the input is proportional to n, because I have n different numbers, and I'm just storing them as bit strings, and I'm only doing comparisons between them. And so the cost is really n times the length of the longest number. So for example, in longest increasing subsequence, there's no such exponential gap. So for edit distance, so let's look at the algorithm in the complexity. So here I'm doing m times n is the cost. M is the number of characters, and the size of the input is indeed proportional to the number of characters. And so this is really polynomial in the input size. Yeah, I'm not taking into account that how many bits I need to store a particular individual character. I'm assuming that's some constant that's hidden in the big O. Okay, and then knapsack, the same question. Yes. Okay. Sorry. Yes, did that one. Could you explain the 3 cases for edit distance? Okay, so I think so let's look here. So here are the 3 cases. Let's suppose I figured out how to perfectly match x1 through xi minus 1, and then with the string y1 through yj. That's what this I minus 1 and j means. So these perfectly match, and then I throw in one more character xi. And then, since I've already matched x1 through xi minus 1 with y1 through yj, I just got to get rid of that guy, and then they match again. So that's why it's this quantity plus 1. Similarly, if I've figured out how to best match x1 through xi with y1 through yj minus 1, and I want to match all the way up to yj, I'll just insert yj. And that's the best I can do. And this says that if I've perfectly matched the first I minus 1 characters of x and the first j minus 1 characters of y, and I want to match the next 2 characters, then if they're the same, I'm done. I don't have to do anything. I just make it longer. And then, but if they're different, I have to substitute yj for xi, and I have to add 1. So these are the 3 ways that I can make the strings xi to through x1 through xi match y1 through yj, and I take the shortest of these 3 costs. That's why I'm taking the min.
Professor, can I ask something?
Please.
So for the longest increasing sequence, I think I'm understanding